The first thing I wanted to show today was, rather than doing another problem, I wanted to show you, I managed to track down some software that generates the diffraction patterns for things. So I want to switch over to that right now. And hopefully now you see something that looks kind of like a bullseye. I see a green border around it, so that should be recording correctly. And what we have here, I don't know if you're in a dark enough place or if your screen resolution will show you this, but right now there's kind of an oval shaped bright blob here in the middle, and you can see some rings around it. This is actually two sources, but I've put the distance between the two sources is very small. And if I increase that distance between the sources, now what I've done is increasing the angular distance between them. We don't usually have the freedom to do that when we're looking at things that are light sources, because they're way the heck out there, and we just don't have that. But whoops, somebody's got their microphone on. Not sure. So you might want to mute yourself, Alex. Anyway, you can see here the diffraction pattern from this point light source and then this point light source. And there's a bright central maximum, and then there's a dark region where the intensity drops down so low enough that we perceive it as no light at all. And then there's another ring around there, and then a dark region and more rings. And so it's similar to the single slit diffraction patterns that we saw, except these are round. I can also show the light intensity curves for these things. And you can see each one, the intensity is at a maximum at the center of the thing, and then it drops to nothing and comes back, but much less bright than the central maximum, and then it comes back again. There are, well, it shows basically red and yellow for each of the two light sources, and then when they're combined, there's green, a green line down there, and you can see that. These are far enough apart that there'd be no problem distinguishing the two, unless we had a telescope or a viewing instrument of a small aperture, and I'm going to decrease the aperture size of whatever it is we're looking at them with. And you can see that if the aperture is too small, you just see a big blob. And so this might be the difference between, I can turn off those light curves, but this might be the difference between a very inexpensive 3-inch diameter telescope and a much more expensive telescope that was used for professional astronomy that might be as big as 10 meters in size, or 8 or 10 meters, or there's an array of telescopes down in Chile that has 4 8-meter telescopes, and they combine the light from those to give a telescope of effectively like an 80-meter diameter thing. But anyway, if you had a larger thing, you'd see those diffraction patterns for them. And we can play with the distance between the sources, decrease that. Eventually, if the distance between the sources is too small, even with a large diameter telescope, it might become difficult to distinguish them as two. In fact, here they're, well, actually, I've more or less merged them together, but there, it's starting to get difficult to tell them apart even with a large aperture. And so I can play with the two things. If I go back to showing the light curves, when you start to get them close enough to where you're starting to see a peak, the red is the combined light from the two. And if that is starting to look, the red line is starting to look more or less like that of a single light source, then the telescope's not going to be able to distinguish it anymore. And if we get here, if all you're doing is collecting light from this thing, you get a nice diffraction pattern. It maybe doesn't drop down all the way to 0 here at the first minimum, but you'd have a hard time telling that there were two objects. You might actually mistake it for a single oval-shaped object, and some astronomical objects are shaped like ovals. Some stars rotate so rapidly that they're noticeably wider at their equator than at their poles, and so that could be an oval-shaped object. So smaller telescopes still, and you get down to here and you have no hope of telling whether it's two objects or one. And so that's what's going on when we're talking about this. But keep in mind that if I increase the distance between these things again and just show the light curves as well, that each of these objects individually will produce a pattern of diffraction on there. And now they're pretty much nicely separated, but the angular separation between the center of this thing and the first minimum, when you're looking at this, you'll be able to measure some sort of an angle there. And that's where that 1.22 lambda divided by d comes from. It'd be the angular separation between this central maximum and this minimum here, or the angular separation down here. I hope you can see my cursor between this point and this point. So that's what's going on with these things. I'm not sure what this one does. Oh, that just changes the scale. And I'm not sure what the point of doing that is. I guess it's just to accentuate some of these things. I wonder if I pull it down that way. Yeah, going this way, I could increase that scale that way. But that's just looking at that. So kind of keep that in mind, and we'll come back and finish off the example problems from the other day. I also typed one out that we'll do that is different as well. Now I should be recording, I hope. Yeah, it is recording, so that's good. Okay. We did this problem and actually this one the other day. So we'll start with this one. At what distance could one theoretically distinguish two automobile headlights separated by 1.4 meters? And assume a pupil diameter of 6 millimeters. So this is going to be the diameter of our viewing instrument. So in the 1.22 lambda divided by d, the capital D is going to be the 6 millimeters, that of somebody's eye. And a dark adapted eye might open to 7 millimeters, but if you've got the light of, say, your dashboard shining into your eyes, you probably don't have your eyes fully dark adapted. You're also looking at headlights bouncing off the road and signs and everything. So your eyes won't be fully dark adapted. And we've got this for the wavelength of the light. Well, these headlights are going to be out here at some distance, and I'll call that distance, I'll just use an...
We're still on the...
Whoops.
like
Okay.
this.
Got to change your back. Thanks. Visualizer, back to that thing. Okay. We're back on that. Anyway, this is the problem we're doing here. And the headlights are separated by 1.4 meters. And I've exaggerated the angle here, but this is what the theta is going to be. And we'll assume here that this 1.4 meters is going to be much less than the distance L. Like this might be thousands of meters. In fact, I'm going to guess it probably will be. And so this will be a small angle. And so we can say that one of the small angle approximations is that technically the radian measure is you would deal with the arc length here, and you'd have the arc length divided by this radius in effect here, and that's what's going to equal this angle theta. But if the angle is small enough, you can use the chord length that separates these two things. And that's, I don't remember how you spell chord in the mathematical sense. If it's C-H-O-R-D or C-O-R-D. Haven't done that since high school geometry, I don't think. But anyway, when you make the angle smaller, there's no difference between, or not a significant difference at all between this straight line and this curved line. And that's the assumption that we'll be going off here. So we'll just say that theta is going to equal 1.4 meters divided by, divided by L, hang on to that pen, and that will equal 1.22 times that wavelength divided by the diameter that we have there. Well, simple fraction left side, simple fraction right side, I can flip both of them, and I'll have L over 1.4 meters is going to equal the diameter of the pupil divided by 1.22 times lambda times, 1.22 times lambda. Okay, or L will equal 1.4 meters, and I think I just multiply it out from underneath. I think I'm going to plug in the numbers here. D, the diameter of the eye, is 6 times 10 to the minus third meters. And then down here, we've got 1.22. Then I'll plug in the wavelength of the light, 580 times 10 to the minus ninth meters. And you can see I've got meters times meters on top and meters on the bottom, so I can divide out one of the meters on top with one of the meters on the bottom. And we'll only have about 1 sig fig here, so not a whole lot of precision, but it's an estimate anyway. Let's see. Yeah, and I actually get about, well, I'm going to round it a little bit. I'd get about 12,000 meters, which is about 12 kilometers, which is somewhere in the neighborhood of 8 miles or so. So I think using a small angle approximation here is justified. We're doing just fine with that. And I think there are hills on I-90 when you're driving along it at night where you can be on top of one hill and it wouldn't be unusual to be able to see 12,000 meters in front of you and cars or trucks coming at you on top of another hill that's that far away. And so you'd be able to see those things from that far away. And I didn't think about it last night while I was driving home, but I probably would have had some situations where the two headlights would have merged into one effectively. So figure 12,000 meters or 12 kilometers, approximately 8 miles. I don't know what 12 divided by 1.6 is. Let's see. That's about 7.5 miles. So that's what that is. Okay, here's one that I ran across in the textbook this morning when I was looking at possible example problems. And it's there's an array of radio telescopes, the very long baseline arrays. I think I've still got a poster in the classroom that has pictures of some of the different telescopes in this array. And they have this is different from the very large array, which is in New Mexico, and that's a network of 27 radio telescopes that are all in a fairly small geographic area. But this one has one radio telescope out on, I think it's on Maui, one of the Hawaiian Islands anyway. And another one, it's got some in Nevada. There's one in California. There's one or two in New Mexico. Let's see, maybe there's one on Kitt Peak. I can't remember for sure. There's one out in the U.S. Virgin Islands in the Atlantic, and there's one in Brewster, Washington. And if you've ever driven up to Omak on Highway 97, oh, let's see, somewhere north of the Columbia River up there, you'll drive by a radio telescope that is part of that array. I've driven over to it before. It's got a fence around it, but it's up there. And all of these, as they record data, they'll be recording it onto hard disk drives. And every week or so, they'll pop out the hard disk and send it down to Socorro, New Mexico, where they combine the signals from all those things. The one thing they have to have is an accurate timestamp. So they've got probably atomic clocks at those things that'll measure time down to the nearest nanosecond or something like that, because to combine them together, you have to take into account the fact that the light will be reaching them at different times because they're on a curved Earth. But anyway, that's the very long baseline array. And the advantage of doing that is you effectively end up with a telescope that's the approximate diameter of the distance between the two most widely separated parts of the telescope. It's not quite that simple, but that's approximately what it is. So you have that. And this has an equivalent diameter of about 8,000 kilometers. So the diameter of the VLBA is 8,000 kilometers. That's roughly 8 times 10 to the 6th meters. Okay. When it's focusing radio waves with a wavelength of 2 centimeters, what would be the diameter of the mirror of a visible light telescope focusing light of wavelength 550 nanometers, so that the visible light telescope has the same resolution as the radio telescope? Well, what we want is for theta radio, or theta VLBA, to equal theta visible. I do this as not this particular problem, but as a problem in the introductory astronomy class, where we try to imagine designing a bunch of different telescopes in different parts of the electromagnetic spectrum, because an important part is that the wavelengths of the light. Radio wavelengths are way longer, 2 centimeters compared to 550 nanometers. And so you have to take that into account. But we can set this equation up here. Lambda vis is what that's supposed to be, divided by the diameter of a visible telescope. And that will equal 1.22 lambda for the VLBA, and this is lambda for the VLBA, divided by the diameter of the VLBA. So we'd like both of these telescopes, or we're just curious to see how big a diameter would we need for a visible telescope to have the same resolution as this one. And might be interesting to see the result. Well, this is a simple fraction. this is a simple fraction. That means I can flip both of them, and I can say that D, and I can also divide out the 1.22s. They show up in each one. So I can say D VLBA over lambda for the VLBA is going to equal the diameter of the visible light telescope divided by the wavelength that it is using. And then it's this that I want to know. So if I just multiply out from under by the wavelength that's used by the visible light telescope, I'll get the diameter of the visible light telescope will equal, I'll get lambda for the visible, the diameter of the VLBA over lambda for the VLBA. And now I can just plug in the numbers. Visible light, that was 550 times 10 to the minus 9th meters. The diameter of the VLBA was 8 times 10 to the 6th meters. So we really only got 1 sig fig on this, but I might push it to 2 like I did on the last problem. And then the wavelength for the VLBA was 2 centimeters, so that's 2.0 times 10 to the minus 2 meters. I can divide out a meter here and a meter there, and I'll end up with a meter 4 units. Well, let's just see what it comes out to. Okay, actually, I get about 220 meters, or maybe just if that 8,000 had 2 sig figs on it, I'd be able to claim that. But anyway, somewhere in the neighborhood of 200 meters for a visible telescope. That's probably a visible telescope that doesn't exist right now. So that's interesting that usually radio telescopes, even when you even though they're huge and you might have a network of them, like at the VLA in New Mexico. I just happened to be there last October, but usually their resolution isn't that great. But in this case, it is pretty darn good. So, but it's huge, and it's using the whole Earth for something like that. One thing that radio waves are used to study is the center of the Milky Way galaxy. There's a whole lot of stuff between us and the center of the galaxy, clouds of gas and dust, and stars, and just all sorts of things. And that absorbs visible light coming from that direction. And so you can't even use visible light telescopes looking in that direction. But radio waves do penetrate that gas and dust. And so astronomers use that, and they like to have good resolution on the thing. So the VLBA might be used for that. Among the things they've discovered is there's a supermassive black hole at the center of the Milky Way with stars and clouds of gas and dust orbiting it at reasonable fractions of the speed of light. So it's pretty amazing what's going on in there. Okay, well, there was that one. All right, now the flag on the moon question. This is always a fun one to do. The Apollo astronauts left a flag on the moon. What's the approximate minimum diameter telescope that can resolve the image of the flag? Well, I'm going to have to grab my textbook to get some astronomy stuff down there. We have to make some estimates here. So let's estimate the size of the flag on the moon. Okay, and imagine that there's this flag up there, and sitting on a pole, something like that. Well, estimated size of this thing, maybe 1 meter. So let's imagine that it's like this. So 1 meter, that's 3 feet, 3.3 feet or something like that. But we're only going to be after one significant figure. Well, how far away is that? That's going to be our angle theta will be end up being this 1 meter divided by however far it is to the moon. And it's a ways. I'm just gonna grab the moon's orbit radius here. Okay. This will be the radius of moon's orbit, which is 384,000 kilometers. That's about, let's see, I think it's about 250,000 miles, maybe. Yeah, it's about 240,000 miles. At one time, we used to have this old car, and my daughters were kind of embarrassed to be driving around in it, actually, or riding around in it. But I'd tell them that we were going to keep that car until we'd driven it to the moon or driven it 240,000 miles. And then it was taking a while to get there, and I realized that it was going to get to the moon at about the time they'd be starting college. And I said, well, we'll probably have to drive it back from the moon too. But we ended up selling it at 250,000 miles. They wouldn't ride it anyway, although all three of them learned how to drive a stick shift driving that thing. So it had a pretty sturdy clutch. All right, but let's figure out the angle there. Theta is going to be this distance divided by that, or 1 meter divided by, well, this ends up being, if I add another 3, I can get rid of the k there. 1, 2, 3, 4, 5, 6, 7, 8. So it's going to be 3.8 times 10 to the 8th meters. And this will be a radian angle here, but I just need the reciprocal of that, I guess. And to 3 significant figures, I'll get about 3 times 10 to the minus 9th radians. And that will equal 1.22 times the wavelength of the light divided by the diameter of our telescope. Well, I can just solve for the diameter of the telescope. It's going to be 1.22 times lambda divided by that angle theta, or 1.22 times, let's just pick the middle of the visible spectrum, 5.5 times, actually it'd be 5.5 times 10 to the minus 7th meters. That'd be 550 nanometers. If I did that. Let's see, divided by our 3 times 10 to the minus 9th radians. And I can get a rough estimate of the size of that telescope. Okay, and I get somewhere, well, I'm getting around 220 meters in diameter again, similar to that previous problem I did for the visible light telescope matching the VLBA, but I'll just call it 200 meters. And it's actually a bit bigger than that. So yeah, our little 8-inch diameter telescopes are not going to be able to see the flag on the moon. Although they have seen the flags on the moon, but not from Earth. There are a whole bunch of spacecraft that are orbiting the moon right now from several different countries. And those things have enough resolution to see the Apollo landing sites from orbit, their orbits around the moon. Moon orbits can be pretty low because they don't have an atmosphere to mess with, so they can do that pretty well. And I've seen pictures that they've taken, and I don't remember a flag. Actually, you'd be looking down vertically on the flag, so it might be hard to see. But you can see footprints that they left on there and the tracks by some of the lunar rovers that they were driving around. So you can see pretty small things. Just didn't happen to notice the flag. Okay, well, we can do one more problem here. This is kind of turning the idea on its head a little bit, but when you have a point source of light and actually it doesn't necessarily have to be a point source of light, but something with a particular diameter, if it's round, it'll make a kind of round spot on whatever it's shining at, and you'll get this pattern that looks like this. And the angular separation between the center of the spot and this thing, that's the 1.22, or the theta min, actually, that you get from the formula. It's the distance there. And if you had a second source, the peaks of those two sources would be separated by the theta min. The difficulty in seeing them is when the peak of one source is sitting on the first minimum of the other source. And that's when it becomes any closer than that, and you can't distinguish them as two objects. So that's the theta min. And this problem says if you send a ruby laser with a wavelength of that outward from the barrel of a 2.7 meter diameter telescope, what would be the diameter of the big red spot when the beam hits the moon 384,000 kilometers away? And we're going to neglect atmospheric dispersion. This, we've been ignoring this because this causes all sorts of problems. Although modern telescopes have ways of compensating for that. So, all right, well, we'll have a theta that ends up equaling 1.22 lambda, there's lambda, divided by d. Well, the d here is 2.7 meters in diameter, but that same angle, this would be the way that the light spreads coming out of that thing, but that same angle is going to show up when we get to the moon, and this will be the radius of the spot there. Here's our angle theta, and we'll just figure out what this radius is, but this would be the radius of the spot. This is our 3.84 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8 eighth meters. And so let's say that theta will equal R divided by 3.84 times 10 to the 8th meters. Okay, and we have to double that angle to get the total width of the round spot that's going to be up there. So let's see. I think we know everything on this side. What we don't know is R. So R is going to equal 1.22 times the wavelength of the light, 694.3 times 10 to the minus 9th meters. times, I'll also have 3.84 times 10 to the 8th meters, and divided by the diameter of the smaller telescope, 2.7 meters. So if you look in here, let's see, 10 to the minus 9th times a 10 to the 8th is 10 to the minus 1, but I've got stuff multiplied together, so may as well just do it and see what we get. Okay, so for a radius, I get about 120 meters. And so the diameter of the spot would be twice that, or about 240 meters. So pretty big. The spot would be, well, longer than 2 soccer fields laid end to end. So pretty big spot anyway. The atmospheric dispersion is something that's dealt with in an interesting way. It's beyond the scope of our course to deal with it, but what they do now at some of the telescopes is, as the light comes through the Earth's atmosphere, it kind of stars twinkle when you look at them. And that twinkling isn't caused by the star, it's caused by the light from the star, which is working its way through the Earth's atmosphere, going through layers at different temperatures, lots of air currents and turbulence and all sorts of things, varying densities of the air. And that makes the starlight twinkle. But what they do is, if they've got a very large telescope, and so this might be something with a 10-meter diameter mirror down there, and usually there's a hole drilled in the center of it, and they have a secondary mirror that's up here, and the light comes down and bounces off that and goes through the hole in the center of it. And then they've got a detector down here, but they will have off to the side somewhere a laser beam that is aimed straight up into the atmosphere in the same direction that the telescope is aimed. And the laser beam will hit light or hit atoms in the upper atmosphere up there along the same light path that the light that goes into the laser is coming in. And it'll bounce back in particular ways. And when it bounces back, they can tell how they need to correct the light that they receive here for the atmospheric effects that are happening straight above it or whatever direction it's aimed in at that instant. And they'll have a part down here, either here or possibly on this secondary mirror. Usually it's down here, and it can change shape rapidly to make up for the atmospheric disturbance or dispersion that's happening at that time. And so they can get more detailed pictures than they otherwise could. In fact, with some of the better methods, this is called adaptive optics, by the way. Some of the better methods, they are starting to get pictures from the ground that are almost as good as what they can take from telescopes in space, like the Hubble Space Telescope or the James Webb Telescope. Now, one advantage the James Webb Telescope has is that it's used for studying infrared light, and that doesn't get through the Earth's atmosphere very well. So you can't study all wavelengths from the surface of the Earth. But for invisible light, like what the Hubble Space Telescope did or studies, they can start to compete with the clarity of the images of the Hubble Space Telescope. The Hubble Space Telescope has it's only a 100-inch diameter, which is a little over 8 feet or 2.5 meters. And so it doesn't have quite the resolving power of a larger telescope. So those big ones on Earth that are starting to compete with it for clarity can gather more light and have a better resolving power, and now they're starting to overcome this effect. So, but the Hubble Space Telescope also has detectors that pick up ultraviolet radiation, which also doesn't get through the Earth's atmosphere very well. So there's a reason to stick those telescopes up there. Okay, we're done a little bit early today. I haven't looked at the survey yet, but I'm planning on having some kind of a question and answer session later this afternoon for the homework that'll be due Friday. I bumped the day forward by one day. And then on Friday, sometime either in the morning or early afternoon, people wanted to have a review session for the test. So we'll do that as well. And so answer those surveys that I sent out in an announcement, and we can pick the times. Does anyone have any questions? Okay, well, we can stop the recording and